Let's talk about rotational motion. And first off, when dealing with rotational motion, recognize that their vocabulary, I can do rotational or angular. And tradition has it that you typically use one or the other adjective. So angular velocity and rotational velocity would be the same thing. Typically, angular velocity is the word. There's something known as rotational inertia, also known as moment of inertia, but rotational inertia is generally the way it's worded instead of angular inertia. And that's just out of habit. But if you said rotational velocity and angular velocity interchangeably, people should know what you're talking about. On the flip side of it, what we've been doing so far is known as linear motion or translational motion. Translational. So you can use these terms interchangeably and you can use these terms interchangeably. Now, for almost every linear or translational quantity that we've dealt with so far, there's a rotational equivalent. So what we're about to do is about to double the number of formulas that we've dealt with so far. So let's start out with basically the list right here. I have various quantities, linear or translational, and then I have rotational or angular. So the position, we'll just use x. Remember, it's x, y, z, r, or s. And then the rotational equivalent is called angle. And the symbol used is a theta. So that is the traditional symbol. And you can use almost any Greek letter. Angles to avoid, or symbols to avoid, don't use pi. I've only seen pi used as a variable to represent an angle once, and it was really confusing, so don't use pi. But almost any other Greek letter works. Theta is traditional. Phi is probably the second one, and then alpha, beta, gamma. But don't use alpha, because we'll use that in a second. Displacement is the change in position, and so we'd have a change in angle here, and this is also called angular displacement. Angular displacement. Although the wording in a problem typically is through what angle does something turn, or how many revolutions does it go. These are all terms of angular displacement. Velocity, we have a v, and then there is the angular equivalent called angular velocity. And the symbol for that is the omega, the lowercase omega. Lowercase. And we've run across this before when we talked about centripetal acceleration, and we had omega squared. That was angular speed, and this is angular velocity. Acceleration, I'm sure you can probably take a guess at what it's called. The symbol over here is A. This is angular acceleration. And the symbol for that is an alpha, or as one student in the past called it, the Jesus fish, but it's really an alpha. So those are the basic ones right there. And so just give a sample of how we're doubling the number of equations. If we went to one of the cake formulas, so let's say delta x equals VIT plus 1/2 AT squared. This is the linear formula here. To go angular, delta theta equals omega IT plus 1/2 alpha t squared. And all we do is we're transliterating. One thing that you pointed out here is that there is another variable that we ignored. So time, which is t, the rotational equivalent is called time. There is no real angular time. The time it takes for something to rotate and the time it takes for something to go straight is still the same time. Average velocity is the change in position over the change in time. So average angular velocity is, and I'm assuming that you would at least, hopefully you've guessed upon the pattern, is the change in angle over the change in time. All right, now there's mass is a linear quantity. When you're talking about at least from an inertial mass, how much force does it take actually to move, to accelerate an object. There is a rotational equivalent. It has actually two names, and I will flip back and forth between them. One of them is moment of inertia, and the other term that seems to be more in vogue now, rotational inertia. And the symbol for it, and this is the first non-Greek letter, the symbol for it is an I. It is not a vector quantity, just like mass is not a vector quantity, but moment of inertia. And this deals with the resistance of an object to rotate, to have angular acceleration. Momentum P has a linear, as an angular equivalent. It's called angular momentum. And I will spell it correctly, angular momentum. And the symbol for this is a capital L. You might sometimes see a lowercase l, and that works as well. But the symbol, if we go back to the formula here, I know that P is equal to mv. Angular momentum is equal to I times omega. There is force, the influence which might cause acceleration. Well, the rotational influence that might cause angular acceleration is known as torque. And the symbol for that is a tau. Now, in my classes, and very few people will catch this reference, I consider this my second most obscure reference. For me, you may also call it G2 Kombuka. And I will not explain that reference. Kinetic energy, we've dealt with so far with the 1/2 mv squared. There is sort of a rotational, and I'll put a little caveat in there in just a second. I know the formula for kinetic energy, as you should know, is 1/2 mv squared, and the rotational equivalent, so we'll put a little r down there, is 1/2 I omega squared. Again, just transliterating. This is angular speed. Now, when we got to this, and I talked about the fact that there are a lot of different formulas for potential energy, all the other formulas have a slight tweak to it. But kinetic energy is the same. You're working on your doctorate or your Nobel Prize winning dissertation or work. That's the formula for kinetic energy. So suddenly I'm saying that there's a second formula here. Well, the issue comes in if I have an object where not everything is traveling the same speed. In other words, if I have something rotating, then so as this pin moves, the tip here is moving faster than a point closer to my hand. And so how do you deal with that? And so what we're going to ultimately end up doing is I'm going to start with this equation here, the classic equation, and derive this one. And in doing so, I will define what moment of inertia is. So this is sort of rotational kinetic energy and 1/2 I omega squared. And those are the basics right there. So we will now work through a couple of basic problems and then eventually get to the good stuff.